Today, we'll present AnthroTAP, Learning Point Tracking with Real-World Motion. In short, AnthroTAP is an automated pseudo-labeling pipeline for point tracking that provides strong, real-world training signals for point trackers. Before we get started, let us quickly recap point tracking because our current projects build on it. Point tracking focuses on establishing correspondences and occlusions of specific points across frames, just like in this video. Formally, the task looks like this. The user picks a query point consisting of an X and Y coordinate, along with the time step of that frame. Given a video sequence with T frames, we predict the trajectory, which is the corresponding point location in every frame, as well as the occlusion probability. Many point trackers learn dynamics from synthetic datasets like Kubrick. This lack of a real-world training dataset has been a long-standing problem in the point tracking literature. The challenge is that point tracking ground truth is extremely hard to annotate. Imagine tracking a person and then tracking a tiny dot on that person's hat across every frame. Doing that for many points is exhausting, so most point trackers have had no choice but to train on synthetic datasets. That motivates the question, what if we build an automated real-world pseudo-label generator? Works like Chrono discuss this limited training data and try to compensate by using real-world knowledge through a pre-trained backbone. CoTracker 3 tries to solve this with self-training. Here, we approach the limitation from the dataset angle. Can we use real-world data directly for training? Human mesh prediction models are extremely accurate these days. We hypothesized that human motion provides a better training signal than synthetic datasets because humans exhibit much richer dynamics, self-occlusion, deformation, and extreme occlusion, especially in multi-person videos like dance. And importantly, this comes from real-world video. So we use an off-the-shelf human mesh recovery model to pseudo-label real-world videos into point tracking training data. Since the output is a mesh, we can treat each mesh vertex as a point trajectory, which makes labeling conceptually simple while still capturing complex motion and visibility. This is the overall pipeline. We use mesh vertices as trajectories. We run an off-the-shelf human mesh recovery model to extract meshes per frame, then project the mesh vertices to the image plane to form pseudo-ground truth point trajectories. To handle occlusion systematically, the pipeline leverages the reconstructed 3D mesh structure, for example, using raycasting to estimate visibility under occlusion. Finally, to reject severe outliers, we use optical flow. We keep only reliable flay based on forward and backward consistency, and use that signal to filter unreliable mesh-based tracks. These are the processed results. For training, we use 48-frame trimmed clips, and we select frames with a stride of 2 to make the motion more challenging and diverse. To evaluate the dataset's effectiveness, we add AnthroTAP pseudo-labeled data on top of synthetic Kubrick and train state-of-the-art point trackers, such as LocoTrack and TapNext. Even using only 1.4 thousand pseudo-labeled real-world videos, tracking accuracy was improved. What's remarkable is that this outperforms CoTracker 3, which uses real-world video in a self-training manner with around 15,000 real-world videos. Our ablation studies also support the hypothesis. Complex, diverse real-world motion provides highly valuable training signals. Someone might wonder, if a point tracker is trained on the AnthroTAP pseudo-labeled dataset, which contains points from humans, can it generalize to non-human points at evaluation time? Surprisingly, yes. In fact, it shows even greater improvement on non-human points. Someone might also ask, pseudo-labels are not perfectly accurate, so is it really okay to use them as a training dataset? To answer this, we conducted an ablation study using Blink Vision, an existing synthetic dataset that contains human motion videos with perfect ground truth trajectories. This setup lets us directly compare two factors in a fair side-by-side manner. Our pseudo-ground truth on real-world videos versus perfect ground truth on synthetic videos. And the result was clear. Real-world visual diversity matters more than annotation precision.
Before we wrap up, let us highlight 3 key takeaways. First, human motion is a powerful and natural source of supervision for point tracking because it inherently contains the non-rigid deformations, articulated motion, and complex occlusions that synthetic datasets struggle to replicate. Second, our results suggest that real-world visual diversity matters more than annotation precision. Even with imperfect pseudo-ground truth, real videos consistently outperform synthetic data with perfect ground truth. And third, with the right structured prior, you do not need massive data. We reach state-of-the-art on TAPvid using only 1.4 thousand videos and 1 day of training on 4 GPUs, which is orders of magnitude less than prior real-world approaches.
That brings us to the end of our talk. Thank you so much for listening.